The light speed isn't fast enough. It's never going to be. We've been given a speed limit that guarantees we'll never see what's out there. You should own the cosmos. Instead, you're staring at an endless void you'll never cross. The universe gave us a speed limit, but it forgot to make the universe small enough for it to matter. If you're curious about these mysteries, make sure to give this video a like. Now let's begin. We live in a universe so vast, so incomprehensibly huge, that even light, the fastest thing we know, struggles to bridge the gaps between the stars. Today, we're going to explore why traveling at light speed, this thing that seems like the ultimate achievement, is actually just the beginning of understanding how truly far away everything really is. We'll look at the real distances involved, the physics that makes this so challenging, and why the universe seems almost designed to keep us isolated on our tiny blue dot. This isn't science fiction. This is the reality of our cosmos, and it's more mind-blowing than any movie could capture. Let's start with something that sounds simple but is actually one of the most profound barriers in all of physics: light speed. 299,792,458 meters per second. In more familiar terms, that's about 300,000 kilometers every single second. In 1 second, light can circle the Earth more than 7 times. That sounds incredibly fast, right? And it is. By human standards, it's almost absurdly fast. Nothing we've ever built comes even remotely close to this speed. But here's where things get interesting. The universe doesn't care about human standards. The distances between stars, between galaxies, between the massive structures that make up our cosmos are measured on scales that make light speed seem almost painfully slow. Think about it this way. Our nearest stellar neighbor, the closest star system to our Sun, is called Alpha Centauri. It's actually a system of 3 stars, and the closest of those 3 is Proxima Centauri. Scientists have measured the distance to Proxima Centauri with incredible precision. It sits 4.24 light-years away from us. 4.24 light-years. That means if you could somehow travel at the speed of light, which, as we'll discuss, is impossible for anything with mass, it would still take you 4.24 years just to reach our nearest neighbor. Let me put that in perspective. If you left Earth today, traveling at light speed, heading toward Proxima Centauri, you wouldn't arrive until the year 2030, and that's our closest neighbor. The next nearest stars, they're even farther. Barnard's star sits about 6 light-years away. Wolf 359 is 7.8 light-years distant. We're talking about journeys that would take multiple years even if you could achieve the impossible and travel at light speed. But wait, it gets worse. Much worse. Those are just the stars in our immediate cosmic neighborhood. Our own galaxy, the Milky Way, stretches about 100,000 light-years from edge to edge. That means even traveling at light speed, it would take you 100,000 years to cross from one side of our galaxy to the other. Think about that for a moment. 100,000 years. That's longer than modern humans have existed on Earth. Longer than recorded history by a factor of 20. And we're still just talking about our galaxy. Just one galaxy among hundreds of billions in the observable universe. Now, before we go further, I need to mention something crucial. When we talk about traveling at light speed, we're already in the realm of impossibility for human beings or any spacecraft with mass. Einstein's special relativity tells us something fundamental about the universe. As you accelerate closer and closer to the speed of light, your mass effectively increases. The energy required to push you faster grows exponentially. To actually reach light speed would require infinite energy. Infinite. That's not a technological limitation we might overcome someday. With better engineering, that's a fundamental law of the universe saying no. But let's imagine, just for the sake of understanding the scale we're dealing with, that we could somehow travel at light speed. Let's pretend the laws of physics took a day off and allowed us to reach this cosmic speed limit. Even with this impossible advantage, we'd still be hopelessly slow when it comes to exploring the universe. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. Traveling at light speed, you'd need 2.5 million years to get there. When you finally arrived, Earth would be unrecognizable. Entire civilizations could have risen and fallen. Our planet might not even be habitable anymore. The distances in the universe are so vast that astronomers had to invent special units just to talk about them without going crazy with zeros. A light year, the distance light travels in 1 year, equals about 9.46 trillion kilometers. 9.46 trillion, that's a 9 with 12 zeros after it, and that's just 1 light year. The observable universe, the part of the universe we can actually see, stretches about 93 billion light-years across. Let that sink in for a second. 93 billion light-years. Even light, traveling at its maximum speed for the entire age of the universe, couldn't have crossed that distance yet if it started from one edge. Actually, that brings up something really interesting. You might wonder, if the universe is only 13.8 billion years old, how can the observable universe be 93 billion light-years across? Shouldn't it only be 27.6 billion light-years across at most, with light having 13.8 billion years to travel in each direction from the Big Bang? This is where things get really cool. The universe itself is expanding, space itself is stretching. While light has been traveling toward us for 13.8 billion years, the space it's traveling through has been expanding the whole time. So objects that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light-years. This expansion means the universe is much larger than you'd expect just from simple math. And here's the real kicker. There are parts of the universe we will never, ever be able to see no matter how long we wait, because they're moving away from us faster than light can travel to reach us. The expansion of space itself isn't limited by the speed of light. Objects can recede from us at faster than light speeds because the space between us and them is expanding. Those distant regions are forever beyond our cosmic horizon. They might as well not exist as far as we're concerned, because no signal, no light, no information from them will ever reach us. The universe is not just vast, parts of it are fundamentally unreachable, isolated by the expansion of space itself. Take a second to subscribe if you haven't already, and hit that thumbs up button. It really helps this channel grow, and it lets me know you want more content like this. I promise we're going somewhere incredible with this. Now, if you're feeling a little bit overwhelmed by these numbers, that's completely normal. Our brains didn't evolve to comprehend distances like this. For most of human history, the farthest horizon we could see was maybe a few kilometers away. Now we're talking about distances that light, the fastest thing in existence, needs millions or billions of years to cross. It's okay if it feels impossible to grasp. In some ways, it is impossible. We can understand it mathematically, we can measure it scientifically, but truly comprehending it on an emotional, intuitive level, that might be beyond human capacity. Let's talk about what happens when you actually try to travel fast through space, because even if we can't reach light speed, we can imagine what getting close to it would be like. And this is where Einstein's theories get really weird and really wonderful. Time dilation. It's one of the most mind-bending consequences of relativity, and it completely changes how we think about space travel. Here's the basic idea. Time is not absolute. It doesn't tick forward at the same rate for everyone, everywhere. Your speed through space actually affects how fast you move through time. The faster you travel, the slower time passes for you relative to someone who's standing still. This isn't speculation or philosophy. This is measured, verified physics. We've tested it with atomic clocks, on airplanes, on satellites, with particles in accelerators. It's real. Imagine you're on that spacecraft again, accelerating to a significant fraction of light speed. Let's say you reach 99.99999% of the speed of light. That's 7 nines after the decimal point. From your perspective inside the ship, time feels completely normal. Your heart beats at its regular pace. You breathe normally. Seconds tick by as they always have. But outside on Earth, time is racing forward at an incredible rate. What feels like 1 year to you on the ship could be hundreds or even thousands of years passing on Earth. The physicist Brian Cox described this beautifully using the Large Hadron Collider as an example. In the LHC, protons zip around a 27-kilometer ring at 99.99999% of light speed. At that velocity, something absolutely bizarre happens to space itself from the proton's perspective. The entire 27-kilometer track shrinks down to just about 4 meters. 4 meters. The universe literally contracts in the direction of motion. This is called length contraction, and it's the flip side of time dilation. Now apply that to space travel. If you were moving at that same speed toward Andromeda Galaxy 2.5 million light-years away, from your perspective on the ship, that distance would shrink dramatically. The journey that would take 2.5 million years according to Earth clocks might feel like just minutes or hours to you. You could theoretically cross to another galaxy within your lifetime. Sounds amazing, right? You could explore the cosmos, visit distant worlds, see things no human has ever seen. But then you return home. You step off your ship, having aged maybe a few years, and everyone you ever knew is dead. Not just dead, gone for thousands, hundreds of thousands, maybe even millions of years. The entire world you left behind has transformed beyond recognition. Civilizations have risen and fallen. Species have evolved and gone extinct. The very continents might have shifted. You've become a time traveler, leaping forward into Earth's future, and there's no way back. This creates what scientists call the twin paradox, though it's not really a paradox once you understand relativity properly. Imagine twin siblings. One stays on Earth. The other boards a spacecraft and travels to a distant star at near light speed, then returns. When the traveling twin comes back, they're younger than their sibling who stayed home. Significantly younger. This isn't just theory. We've measured this effect with atomic clocks flying on commercial jets. The clocks that flew aged slightly less than identical clocks that remained on the ground. The difference is tiny at airplane speeds, just nanoseconds, but it's measurable and it's real. At speeds closer to light speed, the effect becomes dramatic. There's a mathematical relationship that describes this, involving what's called the Lorentz factor. Without getting too deep into the mathematics, the basic formula shows that as your velocity approaches the speed of light, time dilation approaches infinity. At exactly light speed, if you could somehow reach it, time would effectively stop for you. From your perspective, you could cross the entire universe in an instant. But from Earth's perspective, billions upon billions of years would pass. This creates a fundamental problem for space exploration. Even if we could build ships that travel at 99% of light speed, which is itself almost impossibly difficult, we'd be sending people on one-way journeys into the future. They might reach distant stars within their lifetimes, but they could never truly come home. Home would be gone, transformed into a world they no longer recognize. The Global Positioning System, GPS, that you use every day on your phone actually has to account for both time dilation and gravitational effects on time. The satellites orbiting Earth are moving fast enough and are far enough from Earth's gravitational field that time passes differently for them than it does for us on the surface. If engineers didn't correct for these relativistic effects, GPS would accumulate errors of several kilometers every single day. The fact that your phone can pinpoint your location to within meters is proof that Einstein was right about time dilation. Now, you might be thinking about science fiction. You've seen movies where ships travel faster than light using warp drives or hyperspace or wormholes. Are any of those things actually possible? Well, that's a complicated question. Some physicists have explored mathematical solutions to Einstein's equations that might, under very specific and probably impossible conditions, allow for something like faster-than-light travel without technically breaking the rules of relativity. The most famous is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The idea is that instead of moving through space faster than light, which is impossible, you could contract space in front of your ship and expand it behind you. You'd create a bubble of normal space around your ship, and that bubble would surf along a wave of expanding and contracting space-time. From inside the bubble, you're not moving faster than light. Space itself is moving around you. Clever, right? But here's the problem. Every theoretical warp drive design requires something called exotic matter, or negative energy. This is matter or energy with properties we've never observed in nature. It would need to have negative mass or negative energy density. While quantum mechanics suggests such things might exist on extremely tiny scales, we've never seen them in macroscopic amounts. And the quantity of exotic matter required for an Alcubierre drive? According to early calculations, it would be more than the mass energy of the entire observable universe. Later refinements brought that number down, but it's still astronomically large, requiring the energy equivalent of multiple Jupiter masses. Recent research in 2026 has continued to explore warp drive physics, but the fundamental problems remain. A paper, published just last month, examined current warp drive spacetimes and found severe restrictions that make them physically implausible, not just technologically difficult. The researchers noted that when you correctly apply the principles of general relativity, most claims about workable warp drives fall apart. It's not just that we don't have the technology, the universe itself seems to be saying no to this particular loophole. Scientists at institutions like the Limitless Space Institute are still investigating these ideas, looking for any possible way to make faster-than-light travel work within the laws of physics. In 2020, physicist Harold White noticed something interesting in experiments with Casimir cavities, tiny spaces between metal plates in a vacuum. The energy patterns resembled what you'd expect from exotic matter needed for warp drives. They created what they called a nanoscale warp bubble. But we're talking about a bubble 1 micron across. A micron. That's 1/1,000,000th of a meter. Scaling that up to something that could carry a spacecraft? That's a gap we don't even know how to begin crossing. I actually have another video on this channel that goes into more detail about why traveling just 1 light year, let alone faster than light, presents such enormous challenges for humanity. The physics, the engineering, the biological problems of keeping humans alive for such journeys. If you're interested in diving deeper into those specific challenges, check out my video called Why It's Impossible for Humans to Travel 1 Light Year. It really breaks down the nuts and bolts of why space travel is so much harder than science fiction makes it seem. The truth is, based on our current understanding of physics, we're stuck below light speed. And even if we could somehow reach light speed, even if every law of physics bent just for us, we'd still find the universe frustratingly vast. The distances are simply too enormous. Light speed isn't fast enough to make the universe feel small or accessible. It's barely fast enough to explore our own galactic neighborhood within a human lifetime, and even that requires time dilation effects that would separate travelers from everyone they've ever known. So we've established that light speed is the cosmic speed limit, and we've seen how, even at that impossible velocity, the universe remains frustratingly vast. But let's dig deeper into why this speed limit exists in the first place, because understanding that helps us appreciate just how fundamental these barriers are. This isn't like breaking the sound barrier, where we just needed better engineering. This is the universe telling us something profound about the nature of reality itself. Albert Einstein published his special theory of relativity in 1905, and it fundamentally changed how we understand space, time, and motion. The core insight was deceptively simple. The speed of light in a vacuum is constant for all observers, regardless of how they're moving. That might not sound revolutionary at first, but think about what it means. If you're standing still and you measure the speed of a light beam passing by, you'll get 299,792,458 meters per second. Now imagine you're in a spacecraft traveling at half the speed of light, chasing that same light beam. Common sense tells you that you should measure the light moving away from you at only half its normal speed, right? Wrong. You'll still measure it at exactly 299,792,458 meters per second. This constancy of light speed is the foundation of everything else. If light speed is constant for all observers, then something else has to give, and what gives is our intuitive understanding of space and time. They're not fixed, they're flexible. Time dilates, space contracts, mass increases with velocity. All of these strange effects arise from the simple requirement that light speed remain constant. But why? Why is light speed the limit? The answer lies in the nature of mass and energy. According to Einstein's famous equation, E equals mc squared, mass and energy are equivalent. They're two forms of the same thing. When you accelerate an object, you're adding energy to it. And because mass and energy are equivalent, that added energy effectively increases the object's mass. The faster you go, the more energy you add, the more massive you become. And the more massive you are, the more energy it takes to accelerate you further. It's a vicious cycle. As you approach light speed, your effective mass approaches infinity. And accelerating an infinite mass requires infinite energy. The universe simply doesn't have infinite energy available, so you can never quite reach light speed. You can get closer and closer, 99%, 99.9%, 99.99999%, but you can never actually get there. It's an asymptote, a mathematical limit you can approach but never touch. Photons, particles of light, can travel at light speed because they have no rest mass. Zero mass means they don't face the same problem massive objects do. But anything with mass, electrons, protons, atoms, molecules, spaceships, humans, is forever barred from reaching that ultimate speed. It's not a technological problem. It's a fundamental feature of how the universe works. Now, even if we accept that we can't reach light speed, what about getting close? Say 90% of light speed. That's still phenomenally fast by any human standard. The fastest spacecraft we've ever built, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at its closest approach to the Sun. That sounds impressive until you realize it's only about 0.064% of light speed, not even 1/10 of 1%. To reach 10% of light speed would require speeds more than 150 times faster than our current record holder. There's a proposal called Breakthrough Starshot that aims to send tiny spacecraft to Alpha Centauri at about 20% of light speed. The idea is to use powerful lasers to push extremely lightweight probes equipped with light sails. These probes would be about the size of a microchip, weighing just grams. Even with this minimal mass, the energy required is staggering. The laser array would need to be enormously powerful, and the probes would need to be incredibly durable to survive the acceleration and the journey through interstellar space. If successful, and that's a very big if, these probes could reach Proxima Centauri in about 20 years. They'd spend another 4.2 years sending signals back to Earth, meaning we'd get our first close-up data from another star system about 24 years after launch. That's within a human lifetime, which is exciting, but remember, we're talking about probes the size of postage stamps, not humans, not even robots with any significant capability. just tiny sensors that could beam back basic information. Sending humans is an entirely different challenge. A crewed spacecraft would need to be much, much larger. It would need life support systems, radiation shielding, food, water, living space, propulsion systems for maneuvering, and power generation. All of that mass makes the energy requirement skyrocket. Even reaching 1% of light speed with a crewed vessel would require energy on scales we currently can't produce or store efficiently. Let's talk about the rocket equation for a moment, because it's fundamental to understanding why space travel is so hard. The Tsiolkovsky rocket equation tells us that the change in velocity your rocket can achieve depends on the exhaust velocity of your propellant and the ratio of your initial mass to your final mass. In simple terms, you need to carry fuel to accelerate, but that fuel has mass, which means you need more fuel to accelerate the fuel, which adds more mass, which requires more fuel, and so on. It's exponential. For chemical rockets, the kind we use today, the exhaust velocities are limited by the chemistry of the reactions. You can only get so much energy out of burning hydrogen and oxygen, or whatever propellant combination you use. To reach even a small fraction of light speed using chemical rockets would require fuel tanks so enormous that the math becomes absurd. You'd need fuel tanks bigger than planets. Obviously, that's not practical, so we need better propulsion systems. Nuclear propulsion, either fission or fusion, could provide much higher exhaust velocities. A fusion rocket could theoretically achieve exhaust velocities up to several % of light speed, which would make interstellar travel at least theoretically possible within the realm of known physics, but we haven't yet achieved sustained, controlled fusion for energy generation here on Earth, let alone miniaturized it into a reliable spacecraft engine. Fusion propulsion remains firmly in the category of future technology that might be possible someday but isn't available now. Ion drives and other electric propulsion systems offer extremely high exhaust velocities but very low thrust. They can run for months or years, gradually building up speed, but they're limited by power availability. To generate enough power for high-thrust ion propulsion, you'd need either enormous solar arrays which add mass and become less effective far from the sun, or nuclear reactors, which also add significant mass and complexity. Then there's antimatter. When matter and antimatter meet, they annihilate each other, converting 100% of their mass into energy according to E equals mc squared. That's the most efficient energy conversion possible. An antimatter rocket could theoretically achieve very high speeds, possibly up to a significant fraction of light speed, but antimatter doesn't exist naturally in significant quantities anywhere near Earth. We can create it in particle accelerators, but only tiny amounts at enormous cost. As of 2026, the total amount of antimatter humans have ever created would power a light bulb for barely a few minutes. We'd need kilograms of antimatter to fuel an interstellar mission, and producing, storing, and handling that safely is completely beyond our current capabilities. Every propulsion system we can imagine faces fundamental limitations. Either the energy density isn't high enough, or the thrust is too low, or the technology doesn't exist yet, or the fuel requirements are impossibly large. And even if we solve all those problems, even if we develop some amazing new propulsion system that can accelerate a spacecraft to 10 or 20% of light speed, we're still talking about journeys that last decades at minimum. Consider a mission to Proxima Centauri at 10% of light speed, 4.24 light-years at 1/10 light speed equals 42.4 years of travel time. Add time for acceleration at the beginning and deceleration at the end, and you're looking at a journey of 50 years or more. That's longer than most careers. Longer than many lives. Any crew embarking on such a mission would need to be willing to spend the majority of their remaining years in transit, or we'd need generation ships where the descendants of the original crew complete the mission. Generation ships introduce a whole new set of challenges. You'd need a completely closed ecosystem that can sustain hundreds or thousands of people for decades or centuries. Every atom of air, water, and food would need to be recycled with near-perfect efficiency. The social dynamics of such a confined community over multiple generations are impossible to predict. What if people refuse to have children? What if conflicts arise that threaten the mission? What if the systems break down and can't be repaired? And then there's radiation. Space is filled with high-energy particles, cosmic rays that can damage DNA and increase cancer risk. Earth's magnetic field and atmosphere protect us from most of this radiation, but in deep space, you're exposed. The longer the journey, the greater the cumulative radiation dose. Shielding helps, but effective radiation shielding is heavy. And remember, every kilogram of mass makes the propulsion problem harder. There are proposals for using water or other materials as shielding, or creating magnetic fields around the spacecraft, but all of these add complexity and mass. Some people propose using suspended animation or cryogenic freezing to solve the time problem. If we could freeze astronauts for the duration of the journey and wake them up at the destination, the subjective experience would be much shorter. But we don't have that technology either. We can freeze cells and tissues and sometimes bring them back, but freezing an entire human being and reviving them undamaged is science fiction at this point. The ice crystals that form during freezing tear apart cell structures. There's ongoing research into vitrification, a process that turns biological tissue into a glass-like state without forming crystals, but applying that to an entire human body and then reversing it successfully. We're not there yet, not even close. Let's zoom out for a moment and look at the bigger picture, because the challenges of interstellar travel aren't just about physics and engineering. They're about the fundamental structure of the universe itself. And when you start to examine that structure, you realize something both beautiful and sobering. The universe might actually be designed, not by any intelligence, but by the laws of physics themselves, to keep civilizations isolated from one another. Think about the distances we've discussed. Our nearest star is over 4 light-years away. Most stars in our galaxy are hundreds or thousands of light-years distant. Other galaxies are millions or billions of light-years away. These aren't just big numbers. They represent genuine isolation on a scale that's almost absolute. Even if another civilization exists around Proxima Centauri, even if they're technologically advanced and trying to communicate with us, any message they send takes 4.24 years to reach us. Our reply takes another 4.24 years to get back to them. That's a minimum 8.5-year round-trip communication time. You can't have a conversation with that kind of delay. You can exchange information slowly, painfully slowly, but any kind of real-time interaction is impossible. And Proxima Centauri is right next door in cosmic terms. Imagine trying to communicate with a civilization on the other side of the galaxy. Messages would take tens of thousands of years each way. Entire civilizations could rise and fall in the time it takes to send a message and receive a reply. The very concept of communication breaks down at those scales. You're not talking to individuals or even to a continuous culture. You're sending messages into the deep future, hoping someone will still be there to receive them and understand them. This isolation has profound implications. It means that if intelligent life exists elsewhere in the universe, and statistically it seems likely that it does, given the hundreds of billions of stars in our galaxy alone, most civilizations will probably never meet each other. They'll exist in their own isolated bubbles of space and time, separated by distances so vast that meaningful interaction is effectively impossible. Each civilization becomes its own separate experiment in the evolution of intelligence, culture, and technology. We're all alone together, if that makes sense. All part of the same universe, but forever separated by the tyranny of distance and the speed limit imposed by light. The physicist Enrico Fermi famously asked, "Where is everybody?" This question, known as the Fermi paradox, points out the apparent contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for them. We've found no signals, no artifacts, no clear signs that anyone else is out there, but maybe the answer is simpler than we thought. Maybe they're out there, but the universe is so vast and light speed is such an insurmountable barrier that we're all effectively invisible to each other unless we're very, very close and very, very persistent in our attempts to communicate. There's also the issue of time. Civilizations don't last forever. Humans have had radio technology for only about 130 years. That's a tiny, tiny fraction of Earth's 4.5 billion year history. If we last another 1,000 years with detectable technology, that's still just a blink of an eye in geological time. Another civilization would need to be looking at our solar system with the right instruments during that narrow window to detect us. And we'd need to be looking at them during their narrow window of detectability. The odds of those windows overlapping, given the vast stretches of time involved, are frustratingly small. The universe is not just vast in space, it's vast in time. 13.8 billion years have passed since the Big Bang. Stars have been forming and dying for most of that time. The first stars, called Population 3 stars, formed only a few 100 million years after the Big Bang. But those early stars probably didn't have planets with the heavy elements necessary for life as we know it. Those elements, carbon, oxygen, nitrogen, phosphorus, had to be forged in the cores of stars and then scattered into space by supernovae before new stars and planets could form with the right chemistry for life. Our Sun is a third-generation star, formed from material enriched by previous generations of stars. Earth itself is made from the ashes of dead stars. Carl Sagan famously said we are made of star stuff, and he was absolutely right. Every atom in your body, except for hydrogen, was created in the nuclear furnace of a star or in the explosion of a supernova. You are literally made from the remnants of cosmic cataclysms that occurred billions of years ago. That's one of the most beautiful truths science has ever revealed. But it also means that life probably couldn't have formed in the very early universe. There needed to be time for stars to live their lives, explode, and enrich the interstellar medium with heavy elements. So even though the universe is 13.8 billion years old, the window for life might only have opened a few billion years ago. We might actually be among the earlier civilizations to arise, or we might be late to the party. We simply don't know yet. What we do know is that looking out into the universe is also looking back in time. When you look at a star 10 light years away, you're seeing it as it was 10 years ago. When the James Webb Space Telescope observes a galaxy 10 billion light years away, it's seeing that galaxy as it was 10 billion years ago, when the universe was much younger. In February 2026, Webb confirmed a galaxy called MOEMZ14 that existed only 280 million years after the Big Bang. 280 million years sounds like a long time, but in cosmic terms, that's incredibly early. The universe was still in its infancy. What's fascinating is that these early galaxies look different from what astronomers expected. They're brighter, more structured, and seem to have formed stars faster than our models predicted. The early universe was a very different place than astrophysicists thought. This is the beauty of science. When observations contradict predictions, we don't throw out the observations. We revise our understanding. We update our models. We admit we were wrong and figure out what the universe is actually telling us. The expansion of the universe adds another layer of complexity to all of this. Space itself is expanding, and that expansion is accelerating. This acceleration is driven by something we call dark energy, which is honestly just a placeholder name for something we don't understand. We observe the acceleration, we can measure it, but we don't know what causes it. Dark energy makes up about 68% of the total energy content of the universe, and we have no idea what it is. That's humbling. Despite all our technological advancement, despite all our sophisticated instruments and brilliant theories, the majority of the universe is made of stuff we can't explain. This accelerating expansion has consequences for the future of the universe and for the possibility of space travel. Galaxies that are currently far away are getting farther away, and they're accelerating as they go. Eventually, billions of years from now, distant galaxies will be receding from us faster than light can travel through the expanding space between us and them. They'll disappear beyond our cosmic horizon, their light stretched and redshifted into invisibility. Future civilizations, if they arise billions of years from now, might look out and see a much emptier universe than we see today. They might think their galaxy is all that exists because everything else will have receded beyond the observable horizon. Even now, there are galaxies we can see whose light has taken so long to reach us that they're currently far beyond our ability to ever reach, even if we could travel at light speed. The expansion of space has carried them away. We're seeing their ancient light, photons that have been traveling for billions of years, but the galaxies themselves are now so distant that no signal we send could ever catch up to them. They're visible but unreachable, like ghosts of cosmic history. This creates a kind of cosmic loneliness that's hard to articulate. We can see so much of the universe. Our telescopes reveal billions of galaxies, trillions of stars, countless worlds. And yet almost all of it is forever beyond our reach. We can observe, we can measure, we can study and learn and marvel, but we can't touch, we can't visit. We're spectators watching a show that's happening on stages too distant to ever walk upon. Some people find this depressing. The universe is so big and we're so small and isolated. But I find it strangely comforting. It means Earth is precious. This planet, this tiny blue dot orbiting an ordinary star in an unremarkable corner of a typical galaxy, is our home in a profound sense. It's not just where we happen to live. It might be the only place in thousands or millions of light years where life like us exists. That makes every forest, every ocean, every mountain, every living creature precious beyond measure. We're the universe's way of knowing itself, at least in this small corner of space and time. And there's something else. The fact that the universe is so vast and so difficult to traverse means that whatever we do here matters. We're not going to spread across the galaxy in the next few centuries. We're probably not going to make contact with alien civilizations in the foreseeable future. Earth is what we have. The choices we make about how to treat this planet, how to treat each other, how to preserve and protect the biosphere that sustains us, those choices have cosmic significance because this might be all we ever get. This island of life in a vast ocean of space is irreplaceable. Now let's talk about what we can actually see when we look out into this vast universe, because even though we can't travel to distant stars and galaxies, we can observe them. And what we've learned just by looking has been absolutely revolutionary. Every telescope we build, every new instrument we deploy, reveals something unexpected about the cosmos. The universe keeps surprising us, and that sense of discovery is one of the most thrilling aspects of modern astronomy. Consider the Hubble Space Telescope, launched in 1990. For over 3 decades, Hubble has been our eye in the sky, orbiting above Earth's distorting atmosphere, capturing images of unprecedented clarity and beauty. Hubble has observed galaxies forming in the early universe, watched stars being born in clouds of gas and dust, witnessed supernovae exploding across cosmic distances, and revealed the accelerating expansion of the universe that earned its discoverers the Nobel Prize. The Hubble Deep Field images, where astronomers pointed the telescope at what appeared to be empty patches of sky and exposed the detector for days at a time, revealed thousands of galaxies in regions we thought were blank. Every direction we look, we find galaxies. The universe is teeming with them. Then in December 2021, NASA launched the James Webb Space Telescope, the most powerful observatory ever sent into space. Webb observes primarily in infrared light, which allows it to see through dust clouds that block visible light and to observe extremely distant objects whose light has been stretched into the infrared by the expansion of the universe. Webb has already revolutionized our understanding of the early universe, finding galaxies that formed much earlier and much faster than our theories predicted. That galaxy I mentioned earlier, MOEM Z14, observed by Webb as it appeared just 280 million years after the Big Bang, challenges our models of how galaxies form and evolve. It's bright, meaning it contains a lot of stars, and those stars appear to have formed quickly. The conventional wisdom was that galaxy formation was a slow process in the early universe, with small clumps of matter gradually growing larger over hundreds of millions or billions of years. But these Webb observations suggest that at least some galaxies assembled much more rapidly. The universe in its infancy was apparently capable of creating large, bright galaxies faster than we thought possible. This is a perfect example of how science works at its best. We develop theories based on the best available evidence. We make predictions about what we should observe. Then we build better instruments and actually look. When the observations don't match the predictions, we don't insist the universe must be wrong. We revise our theories. We go back to the drawing board and figure out what we misunderstood. Sometimes this means small adjustments to existing models. Sometimes it means fundamental rethinking of our assumptions. Either way, we learn. We get closer to understanding reality as it actually is, not as we assumed it must be. Ground-based telescopes have also become incredibly sophisticated. The European Southern Observatory operates the Very Large Telescope in Chile, which, despite its somewhat uninspired name, is actually an array of 4 separate 8.2-meter telescopes that can work together as an interferometer, effectively creating a much larger instrument. The Atacama Large Millimeter Array, also in Chile, consists of 66 radio dishes working in coordination to observe the universe at millimeter and submillimeter wavelengths. These wavelengths reveal cold gas and dust, the raw material from which stars and planets form. ALMA has captured stunning images of protoplanetary disks, the swirling disks of gas and dust around young stars where planets are being born. We can actually watch planetary systems forming in real time, or at least in cosmic real time, which spans millions of years. These observations have shown us that planet formation is common, probably the default outcome when a star forms. Most stars seem to have planets. That's a relatively recent discovery, and it's fundamentally changed our perspective on how common planetary systems are. The first confirmed exoplanet orbiting a Sun-like star was discovered in 1995. Just 1995, that's barely 30 years ago. Before then, we knew planets existed around our Sun, but we didn't know if that was unusual or common. Now, as of 2026, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting confirmation. We've found planets of every imaginable type. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Super-Earths larger than our planet but smaller than Neptune. Ice giants, rocky worlds, planets orbiting binary star systems, even planets orbiting the dead remnants of stars called pulsars. Some of these planets orbit in the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it, so these habitable zone planets are of particular interest in the search for extraterrestrial life. Proxima Centauri, our nearest stellar neighbor, has at least 3 confirmed planets. One of them, Proxima Centauri b, orbits in the habitable zone. It's only slightly more massive than Earth. Could there be life there? We don't know. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun, and it's prone to violent stellar flares that could strip away a planet's atmosphere or sterilize its surface. But maybe life could adapt. Maybe subsurface oceans could be protected from the radiation. We simply don't know enough yet. The tantalizing thing is that Proxima b is right there, astronomically speaking, 4.24 light-years away. If we could send a probe at 20% of light speed, like the proposed Breakthrough Starshot mission, we could get close-up data from another potentially habitable planet within a human generation. That's extraordinary. For the first time in history, we can seriously contemplate sending instruments to another star system and getting results back while the people who launched the mission are still alive. But even that requires technology we don't have yet. The lasers needed to propel the light sails would need to be incredibly powerful, probably in the gigawatt range. The sails themselves would need to be large, lightweight, and able to survive the intense laser light and the impact of interstellar dust particles at relativistic speeds. At 20% of light speed, even a tiny grain of dust hits with enormous energy. The probes would need to be hardened against radiation, able to operate autonomously for decades, and equipped with instruments sensitive enough to gather useful data during a high-speed flyby of the target system. And there's no slowing down. At 20% of light speed, you don't have enough energy to brake. You get one pass through the system, lasting maybe hours or days, and then you're gone, flying off into the depths of interstellar space forever. You have to gather all your data in that brief window and transmit it back to Earth using a tiny power source, probably nuclear, sending a signal across 4.2 light-years of space. The engineering challenges are immense, but they're not necessarily impossible. That's the difference between this and faster-than-light travel. Breakthrough Starshot is incredibly difficult, but it doesn't violate the laws of physics. Meanwhile, we continue to study the universe from our home in the solar system, and what we're learning is remarkable. We've mapped the cosmic microwave background, the afterglow of the Big Bang itself, with exquisite precision. This faint microwave radiation fills all of space, slightly warmer in some directions and slightly cooler in others. Those tiny temperature variations, just millionths of a degree, represent the seeds of all cosmic structure. Regions that were slightly denser than average collapsed under their own gravity to form the first stars and galaxies. Regions that were slightly less dense became the voids between galaxy clusters. By studying the cosmic microwave background, we can learn about the conditions in the very early universe, just 380,000 years after the Big Bang. Before that time, the universe was too hot and dense for light to travel freely. It was opaque, a fog of ionized plasma. But when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, light could suddenly travel freely. That light has been traveling ever since, stretched and redshifted by the expansion of the universe, and we detect it now as microwave radiation. We're literally seeing the baby picture of the universe. Projects like the Planck satellite and the Wilkinson microwave anisotropy probe have mapped this radiation in incredible detail, allowing cosmologists to measure the age of the universe to high precision, 13.8 billion years, and to determine the composition of the universe. About 68% dark energy, 27% dark matter, and only 5% ordinary matter, the stuff that makes up stars, planets, and us. We're a tiny minority in the universe. Most of the universe is made of things we don't understand. Dark matter is particularly mysterious. We know it exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. There must be additional mass we can't see. Galaxy clusters show similar effects, and the patterns in the cosmic microwave background require dark matter to explain them. But we don't know what dark matter is made of. It's not ordinary atoms. It doesn't emit, absorb, or reflect light. It interacts with ordinary matter almost exclusively through gravity. Physicists have proposed various candidate particles like WIMPs, weakly interacting massive particles, or axions. But despite decades of searching, we haven't directly detected dark matter particles yet. Dark energy is even more puzzling. It behaves like a property of space itself, a kind of energy that's uniformly spread throughout the universe and causes space to expand at an accelerating rate. Einstein's equations of general relativity actually allow for such a thing called the cosmological constant, but Einstein himself thought it was a mistake. Now it appears he was right all along, though for reasons he didn't anticipate. The universe's expansion is accelerating, and we need something like a cosmological constant to explain it, but we don't know why it has the value it does or what it fundamentally represents. These mysteries, dark matter and dark energy, remind us that despite our incredible technological progress, despite all the amazing discoveries of the past century, we're still fundamentally ignorant about most of the universe. And that's not a failure, that's an opportunity. Every mystery is an invitation to explore, to question, to investigate. Science isn't about having all the answers, it's about asking better questions and developing tools to answer them. One of the most powerful tools we have for understanding the universe is mathematics. When physicists talk about theories like general relativity or quantum mechanics, they're describing the universe in the language of mathematics. Einstein's field equations of general relativity are mathematical expressions that relate the curvature of space-time to the distribution of matter and energy. Those equations are beautiful in their elegance, and they make precise predictions that we can test. When we observe light bending around massive objects, or time running slower in strong gravitational fields, or black holes merging and sending ripples through space-time, we're seeing Einstein's mathematics made manifest in physical reality. Speaking of black holes, let's talk about them for a moment, because they're some of the most extreme objects in the universe, and they're deeply connected to our discussion of light speed and cosmic distances. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. The gravity doesn't just slow light down, it traps it completely. The escape velocity at the event horizon equals the speed of light, and since nothing can travel faster than light, nothing can escape. Black holes form when massive stars, at least several times the mass of our Sun, exhaust their nuclear fuel and collapse. The core implodes in a fraction of a second, and if the mass is sufficient, nothing can stop the collapse. The matter compresses down to infinite density at a point called the singularity, though that's almost certainly a sign that our current theories break down at those extreme conditions. We need a theory of quantum gravity to properly describe what happens at the singularity, and we don't have that yet. What we do know is that black holes are real. We've detected them indirectly through their effects on nearby matter, and in 2019 the Event Horizon Telescope collaboration released the first actual image of a black hole's event horizon. Well, technically the image shows the shadow of the black hole against the glowing accretion disk of hot gas swirling around it, but it's still remarkable. They imaged the supermassive black hole at the center of the galaxy Messier 8755 million light-years away. 55 million light-years. Think about that. The light in that image left that galaxy before the dinosaurs went extinct. We're looking deep into the past. In 2022, the Event Horizon Telescope team released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. It's about 27,000 light-years from Earth and has a mass of roughly 4 million suns. It's relatively quiet right now, not actively consuming large amounts of matter, but occasionally something gets too close and we see flares of X-rays as material is torn apart and heated to millions of degrees before disappearing beyond the event horizon. Black holes also connect to gravitational waves, another prediction of Einstein's general relativity. When massive objects accelerate, they create ripples in the fabric of space-time itself. These ripples propagate outward at the speed of light. For most situations, gravitational waves are incredibly weak, far too weak to detect. But when two black holes spiral into each other and merge, or when two neutron stars collide, the gravitational waves produced can be strong enough to detect here on Earth. In September 2015, the LIGO observatory detected gravitational waves for the first time in history. The signal came from two black holes, each about 30 times the mass of our Sun, that had been orbiting each other and gradually spiraling inward for billions of years. In their final moments, they were orbiting each other hundreds of times per second, moving at a significant fraction of light speed before merging into a single larger black hole. The energy released in that merger was staggering. For a brief moment, the gravitational wave signal from that merger was more powerful than all the light from all the stars in the observable universe combined, and we detected it as a tiny, tiny distortion in space-time, stretching and squeezing the arms of the LIGO detectors by less than the width of a proton. Since that first detection, LIGO and its partner observatory Virgo have detected dozens of black hole mergers, neutron star mergers, and other cataclysmic events. Each detection tells us something about the population of compact objects in the universe, how common they are, how they form, how they evolve. And each detection is a direct confirmation that Einstein was right about the nature of gravity and space-time. The fact that gravitational waves travel at the speed of light is important. It tells us that gravity isn't instantaneous. If the Sun suddenly vanished, we wouldn't feel the loss of its gravitational pull for 8 minutes and 20 seconds, the same time it takes light to travel from the Sun to Earth. Gravity and light both travel at the cosmic speed limit because both are disturbances in fundamental fields that propagate through space-time. Now here's something mind-bending. Because gravitational waves travel at light speed, they face the same limitations we've been discussing. When LIGO detected that first black hole merger in 2015, the event had actually occurred 1.3 billion years earlier. 1.3 billion years. When those black holes were spiraling into each other, life on Earth was still single-celled organisms. Complex multicellular life hadn't evolved yet. The signal traveled across 1.3 billion light-years of expanding space, gradually weakening until it reached Earth and caused detectors in Louisiana and Washington state to twitch by an amount smaller than an atomic nucleus. Every photon of light, every gravitational wave, every particle that reaches us from distant parts of the universe has been traveling for immense periods of time. Astronomy is inherently the study of the past. We can never observe the universe as it is right now, only as it was when the light or other signals we detect were emitted. For nearby objects, the delay is trivial. The Moon is just over 1 second away by light travel time. The Sun is 8 minutes and 20 seconds away. Even Proxima Centauri at 4.24 years is relatively close. But when we observe distant galaxies billions of light-years away, we're seeing them as they were billions of years ago, when the universe was younger, when the first stars were forming, when the cosmic story was just beginning. This creates a strange situation. Somewhere out there, perhaps billions of light-years away, there might be astronomers looking at the Milky Way, but they're not seeing it as it is now. They're seeing it as it was billions of years ago, before the Sun formed, before the solar system existed, before Earth coalesced from the primordial disk of gas and dust. To them, if they exist, there's no Earth yet, no life, no humans. just a younger version of our galaxy, different in structure and composition from the galaxy we inhabit today. And if we somehow sent a signal to them right now, it would take billions of years to arrive. By the time it reached them, both our civilizations, if theirs exists at all, might be long gone. The timescales involved are so vast that they make communication across cosmic distances almost meaningless. You're not exchanging information with contemporaries, you're sending messages to the distant future and receiving messages from the distant past. Some scientists have proposed that this is actually the solution to the Fermi paradox. Maybe there are many civilizations out there, but they're so spread out in space and time that they rarely overlap in ways that allow for detection or contact. Maybe civilizations typically last only a few thousand or tens of thousands of years, which is a blink of an eye in cosmic time. Maybe by the time the light from one civilization's activities reaches another star system, the originating civilization has already collapsed or evolved beyond recognition. There's also the problem of recognizing signals as artificial. When we search for extraterrestrial intelligence, we're looking for patterns that seem unlikely to occur naturally. Regular pulses, narrowband radio emissions, geometric structures, anything that screams deliberate construction rather than natural process. But what if advanced civilizations use communication methods we can't detect or don't recognize? What if they've moved beyond radio and optical signals to something more sophisticated like neutrino beams or quantum entanglement communication? If that's even possible, we might be like someone in the year 1800 looking for smoke signals while everyone around them is using telegraph wires. We're searching with the tools and concepts we have, but an advanced civilization might use technologies so far beyond ours that their signals pass right through our detectors without leaving any trace we'd recognize. It's humbling to consider that we might be swimming in a sea of alien communications and not even know it, because we lack the conceptual framework to understand what we're looking at. The search for extraterrestrial intelligence, SETI, has been scanning the skies for decades now, listening for signals at various radio frequencies. The most famous search was probably the Big Ear radio telescope's detection of the WOW signal in 1977, a strong narrowband radio signal that lasted 72 seconds and has never been detected again despite repeated attempts to find it. Was it aliens? Probably not. It was most likely some kind of terrestrial interference or a natural astrophysical phenomenon we don't understand yet. But it captured imaginations because it was exactly the kind of signal we think an alien civilization might send. More recently, searches have expanded to include optical SETI, looking for brief flashes of laser light that might be attempts at communication, and efforts to detect techno-signatures, evidence of advanced technology like artificial structures around stars or industrial pollution in exoplanet atmospheres. So far, we've found nothing definitive. Every candidate signal has either turned out to be terrestrial interference, natural astrophysical phenomena, or remained too ambiguous to draw conclusions. If you made this far, I am sure you will love this other video at the left side of the screen. How long until humans achieve interstellar travel? Humanity has a deadline. Whether climate catastrophe, asteroid impact, or the eventual death of our sun, Earth won't be habitable forever. If we want to survive, we need to reach the stars. See you there.